But we'll get one for you in a second. All right, here we go. So wrapping up yesterday's discussion, number 10. It says, suppose the vector S has a magnitude 55 and makes an angle of 213 degrees with the positive x-axis. Measure counterclockwise when S is in standard position. Write S in the form S equals AI plus BJ. So we've got a magnitude 55 and an angle of 213 degrees. I guess if we wanted to write that in standard notation, it would be parentheses 55, comma, 213 degrees. What was the first thing that we do in every single vector problem, class? Draw a picture. All right. Which quadrant are we in, class? Third quadrant, I heard it there. 180, 270, 213, somewhere in between there. So 213 degrees, and this is a magnitude of 55. If you want to say R equals 55, that's fine. And what they're asking us to do is to put it into AI plus BJ form. In other words, find the A and the B, where the A is the X component and B is the Y component. If you want to give letters for those, you could call the X component SX and you could call the Y component SY. Alright? The 213 is helpful to some extent, but if you remember yesterday, what we found is really helpful is that reference angle right in there. So it's just gonna, if you want to make a list of like sort of steps, obviously on this one it's going to be draw the picture. Step number 2 is going to be find the reference angle. So find theta ref. In this case, we know that the whole way, all the way around here is 213. We know that just up to this line right here is 180. So in this case, our theta ref is going to be 213 minus 180. Those of you with calculators, any number there? Say again? 33 degrees. If you want to redraw that picture, you can. I mean, it's this picture, you've got SX. This isn't actually very much bigger than that. So, but that's the picture that we have. And 55 right here. And this is literally just you have a triangle with an angle and one side. Go ahead and find those other sides. Mr. Ginsler, do you have the handouts from yesterday, Vectors 3? If you can find one of those, Preston needs a copy. All right, so let's go ahead. If we want to find SX, we need to write a trig equation that's going to relate this angle, SX, and 55. And here's a hint. You want to use sine or cosine. We'll remember if you want to play the game, write the arrow across and there's your opposite. Got a leg right next to it that's adjacent. So if I'm looking for SX, I need something that relates the adjacent and the angle and possibly the hypotenuse. Cosine sounds pretty good. So cosine of 33 degrees equals SX over 55. Multiply both sides by 55, you get SX equals 55 cosine 33 degrees. I await your calculator answer. Say one more time.
46.13.
I hear 46.13. Do we have agreement? Okay. What about SY? What trig equation shall we use for that one? What trig ratio? Sine. So we'll say sine of 33 degrees is going to be the opposite over hypotenuse. So SY over 55. Multiply both sides by 55, same kind of thing we did up there. So 55 sine of 33 degrees. Calculator says that answer is
29.96.
I hear 29.96. Are we in agreement?
Yeah.
Okay. So it seems to me that we could probably just put those numbers in. So 46.13 times vector I plus 29.96 times vector J. except that is not the correct answer.
Uh-oh.
You need to just do a reality check. It's just a quick little thing. Is this really 46.13?
No,
No, what's wrong with it?
it's positive or negative.
In our picture right here, if you were to think about the direction, this is moving to the left and this is moving down. So this is something that your calculator will tell you that this is the answer, and your calculator is right after a fashion. It is right that that is the length of this. Okay? But with vectors, we're not concerned just with length, we're also concerned with direction. Okay? So our pre-calculus knowledge is going to come into play here. So I skipped number 3. Number 3 is cosine and sine to find the x and y parts. But then step number 4 is check the plus or minus, check the sign SIGN, okay? Check the sign. Positive or negative, doesn't need to be positive or negative. In this case, my pre-calculus knowledge says when I'm going to the left, then that x value is negative. And when I'm going down, that y value is negative. I could put a negative right here, or I could just put a minus right there. Okay? So your calculator is good, but it's not good enough. You might just be like, just plug in the number. No, that's you got to do a reality check there. Okay? So check the sign, plus or minus. Let's look at number 11 there. This is today's assignment, so this is not quite what we need just yet. But y'all got it there in front of your paper. Find the vector 5u minus 2v given the vectors u equals 9i minus 4j and v equals negative I plus 7j right here. Now this ought to be pretty straightforward. So they're looking for 5u minus 2v. You're told that u is equal to 9i minus 4j and v equals negative I plus 7j. So this is where vectors kind of start to look like algebra, and for all practical purposes, this is like first month of algebra here. Alright? So 5u would mean 5 times 9i minus 4j minus 2 times vector v, and vector v is negative I plus 7j. Stop. That look about right? That's on your paper? Okay. Thank y'all. So one of the reasons why we do this AI plus BJ thing is because our algebra skills, like distribution, can readily apply here, okay? This is a scalar times a vector. And remember, if you have a scalar times a vector, it's just going to be the scalar multiple times the x part, the scalar multiple times the y part. So this is just going to be 5 times 9i, so 45i. 5 times negative 4j, so that's going to be negative 20j. This is a negative 2 times a negative 1, so it's going to be a plus a 2i. A negative 2 times the positive 7j is going to be a negative 14j. And then absolutely, your algebra skills continue. You're like, oh, those are like terms. And with vectors, which is what these are representing, the x parts, if you remember when you're adding vectors, you add the x parts and you add the y parts, okay? So we're just going to combine the 45 and the 2 and get a 47i, and then the negative 20j and negative 14 is going to give us negative 34j, and we'll call ourselves complete. All right, and that should be enough for you to take care of those next couple problems. All right, everybody good? Alright, let's move on to the next thing, which is actually applying vectors and how that relates to forces and things like that. So go and get a brand new sheet of paper. We're going to talk about vector applications. So this vector is for vector applications. What we're going to talk about is what happens if you have two forces, we'll call them F1 and F2, both acting on the same object. And for this, we're going to have Robert come up here again and do a little demonstration with him. Y'all may have forgotten what the result of this is. So, one of the reasons why we talk about vectors is because vectors are a way of representing forces, okay? Where are forces used? Well, just pretty much anything that's moving. So if you're going to be involved in making anything that moves, then you're going to have deal with forces and vectors. If you make anything that doesn't move, like let's say maybe like a building, okay? You don't want it to move. And so you want all those forces to balance out. You want the force that's pushing this way on your building to be the same as the force that's pushing this way on your building. Otherwise your building will move, and that would just be a really bad day for lots of people, okay? So forces are a way that we, utilize vectors. There's lots of other ways, but this is the easiest way, and it's probably something. How much have y'all seen forces in physics? A little bit, a lot, decent amount. Okay, so it's all something you can kind of relate to in the studio. So when two forces act at the same time on an object, what happens is actually you can treat it as like one new force, okay? All right, and I'm not just excited about force because of Star Wars, the trailer dropping yesterday, but anyway, that's beside the fact. We're actually using force push, real force push, all right? So he's gonna push that way, and I'm gonna, we'll do it separately, then we'll do it together, and then we'll see what kind of happens, all right? So he pushes that way independently, all right? Leave it be, all right? And then separately, independently, I'm going to push it this way. All right, Dominic, come up here. You're going to be our resultant jurors, okay? So, you can stay off to the side for right now for saying Dominic. So, what happens is that when Robert and I both push together, what do y'all think is going to happen to the chair? Think it's going to go diagonal? Okay, so ready? And now, you got hands flat? All right, you know what's going on. All right, ready, set, go. Wow. All right, pretty neat, huh? Now, what's interesting is the chair traveled along the same line and got to the same point as if one person called Mr. Resultant, come on over here, Mr. Resultant, had done that force. So go ahead and now, you were the resultant. You are going to just push it diagonal, just, there you go. All right? So the thing is that what Dominic is doing is basically the equivalent of Robert and me pushing together. Okay? So that's what we're going to talk about. Good job, guys. Thank you. So what does that all have to do with this? Well, let's say that you've got two forces that are both acting on an object. Okay? What you can do is you can figure out what the resultant force is by adding them together and then just finding their sum. So we'll go ahead and summarize that. So two forces are acting on an object. You can calculate their sum namely, it's called the resultant. By adding their components. Then, find the magnitude and direction of the new vector. So if I've got two forces that are pushing on an object, they're both applied right here to this object here. And I want to figure out, okay, what's going to go on with this object, with this chair, or maybe this is the top-down view. You've got some car which has a force from the gas pedal and exerting on the wheels, just going this way, but then you also have maybe another force coming in here. I don't know, maybe a semi hit it. More of an example then. What's going to happen with the car, okay? So what's going to happen with our object? What's the path that it's been traveling? So what we're going to do is you draw force 1. Then at the tail end of that, you draw force 2. And like we've been seeing, our resultant is force 3. What we've seen is that you can break down force 1 into its x component. I'll call that force 1x. And its y component, I'll call that force 1y. You can break force 2 down into its x and y parts. I'll call that force 2x and force 2y. And what we've been saying all along, the really neat thing about forces is that new vector, force 3, has an x and a y, force 3x, and force 3y. And its x and y parts are the combination of the x part of force 1, the x part of force 2, and the y part of force 1 and the y part of force 2. So here's how we can say that. So force 3 in the x direction equals force 1 in the x direction plus force 2 in the x direction. Force 3 in the y direction is equal to force 1 in the y direction plus force 2 in the y direction. So if you were to write vector 3 in component notation, you might say its x part is f1x plus f2x. Its y component is f1y plus f2y. Since we talked about AI plus bj form, you could say, f1 plus f1x plus f2xi plus f1y plus f2yj. But I'm not gonna go. All right. So that's great for component form, but a lot of times what we're interested in is not what's the x and y of it, but rather what's the magnitude and what's the direction. Okay. So in Dominic's case, he would be like, well, what direction do I push it in? It's kind of, maybe he wasn't quite sure there initially until I told him we need to push it in that direction. Okay. And then the question might be, well, how hard do I push it? What's the magnitude? Okay. And that's going to be based on this. So let's just talk about it real quick, class. If you had F3, force 3, and you have a force 3 in the x direction, and you have a force 3 in the y direction, what might be a way that you could calculate, we'll call this the magnitude. What's going to be our formula for going from the x and y component to the magnitude? Pythagorean theorem. Yeah. So we're going to get used to writing absolute value bars. Now I'm going to see if y'all are comfortable with my super shortcut way of writing Pythagorean theorem, okay? Instead of saying this squared plus this squared equals this squared, and then take the square root, watch what I'm going to do here. I'm going to say the magnitude of f3 is equal to the square root of f3x squared plus f3y squared. See if that makes sense to you. I know y'all are probably all about shortcuts and stuff like that. This is kind of a shortcut. Does that make sense? Because you normally would square it and be like this squared, this squared, this squared. But now it's sort of like I can just type that in a calculator and go. I think that's what we're writing down. What about the direction? Okay. I'm normally concerned with theta. And here's where things get a little dicey. I wish I could give you a formula for theta that's going to work every single time. Okay? I really wish I could, but I can't. All right? And I'll try to explain to you real quick why. The reason why I can't just say that theta is inverse tangent of y over x is because sometimes you're going to be in different quadrants. Okay? And inverse tangent is only going to give you the first quadrant and fourth quadrant answer. I'll say that one more time. If you don't get it, that's fine, because I'm going to show you something that I'll give you a workaround here. But the thing is that we don't know which quadrant you're going to be in, and the tool that we're going to utilize to find the theta is inverse tangent. Inverse tangent only gives you fourth quadrant and first quadrant answers. And if your vector, when I add these two things, they add to the second quadrant or third quadrant, then it's not going to tell you what it's not going to give you that answer. And that's a problem. All right. So the shortcut, well, it's not a shortcut, but the way of arriving at it is just literally to think about what are the situations that we might run into and use your head. All right. When you're adding two vectors, it's going to end up being in one of four quadrants. You're either going to be here, or you're going to be here, or you're going to be down here, or you're going to be along the axis, I guess. But your resultant is going to be in one of those. And in each case, you're going to have a y and an x. You're going to have a y and an x. There's a y and an x. Y and an x. I'll make this one the same one as that one. Okay, so you'll have a y and an x. All right. Here's what you need to do. So if you're in this quadrant, then this is your angle. If you're in second quadrant, then that's your angle. If you're in third quadrant, that's your angle. And if you're in fourth quadrant, that's your angle. Okay, that's your theta in terms of standard notation. I cannot give you a generic formula for theta because of what I said, the limitations on inverse tangent. However, I can give you a formula for theta ref. Right? Where if you're in the first quadrant, theta ref is right there. If you're in the second quadrant, theta ref is right there. If you're in the third quadrant, theta ref is right there. And if you're in the fourth quadrant, theta ref is right there. I can give you a formula for theta ref, okay? And then theta equals, well, it just depends on the quadrant and you using your head. Let's think about if I'm in this quadrant right here, theta ref, I can calculate that with the y and the x, inverse tangent. If I'm over here, if I'm looking for this angle right there, inverse tangent, y over x. If I'm in this quadrant right here, y over x, inverse tangent will help me out here. If I'm in this quadrant right here, theta ref, y over x, that's what's going to give me that angle. So the reference angle is the inverse tangent. I'll say, rather than just saying y over x, I'll say force 3y divided by force 3x. And I'll put absolute value bars around it to make sure that we're always dealing with those positive angles, or those positive lengths. Mr. Greenspan, we need a password on that one. more thing. I'm going to write it over here on this other board before we move to solving some problems. On the thing that I erased there a minute ago, we noticed that if you have force, force 1, force 2, add up the x, add up the y's, okay? Sometimes you just need to add up the x parts, or the x components, and the y parts, namely the y components. And in mathematics, we have a special way of denoting that. We'll say this symbol right here, it's sigma, capital sigma, Greek letter, and what that means is sum, or add up. Add up all the fx's, all the x parts, right? So that would be like f1x plus f2x plus f3x, I don't know, maybe it depends on how many vectors we have here, plus dot dot dot. That's what this symbol right here means. It means add them all up. Add up all the x's, okay? So you add them all up, and what you get, now this is almost sort of like a business term here, okay? Is something called the net. Have y'all ever heard the phrase like the net and the gross, okay? If you haven't, then when you get to economics next year as a senior, if you're a senior, you might see that. Net and gross, net means what you get at the end. Sort of like if you have a business and you spend $100, to get all your equipment, but then you make $115, okay? You might be like, I made $115. I made $115. Like, yeah, wait a second. You spent $100 just to get all that equipment. You know, if it's a lemonade stand, like the lemons and the sugar and the ice and the water and all that stuff like that. So your net is 15. Okay, so how much you have at the end of all that? So we would say F net in the x direction. Has Mr. Brandt talked to y'all about the net force and that stuff like that? Okay, so that's not too unfamiliar. Just because I can't resist myself, I will tell you that there was a famous man, famous in both science and math, and he realized that the net force on something, if you have a bunch of forces adding them all up together, okay, then that net force is actually equal to that object's mass times its acceleration in that direction. We're not really going to deal with that a lot, but in case you're wondering where this kind of stuff comes from, anyway, this is a thing. If you end up being an engineer, you do this a whole lot in physics 1, physics 2, statics, dynamics, and stuff like that. And you'd say the summation of forces in the y direction, that's F1y plus F2y plus F3y, however many forces you have, equals F net y, that's the net force in the y direction, or actually let's call it F netting. And that's going to equal your mass times your acceleration in the y direction. We will utilize this notation a little bit as a way of kind of helping us keep things straight. All right, I think y'all have a problem there, right? Get the paper? Let's go ahead and apply all this stuff. This says, suppose an object is positioned at the origin. A force, F1, of magnitude 45 newtons acts on the object at an angle of 33 degrees. Okay, so we've got that right there. A force F2 of magnitude 75 newtons, so it's kind of the scale, acts on the object at an angle of 322 degrees with the positive x-axis. Okay? Let F, I call it F3, but they say big F, equals F1 plus F2 be the resultant force. Find the following: the magnitude and its direction, where namely its direction is the angle between 0 and 360. Okay? So literally all we have to do is add those two vectors together, okay? So where F1 is 45 newtons at 33 degrees, and F2 was 75 newtons at 322 degrees. And if I were to kind of draw that on here, so I'm going to draw F1 and then draw F2. So my resultant force, if I were just kind of to guess, which is always kind of a good idea to estimate at the beginning, I'm going to guess it's going to be a little bit longer than 75, okay? And definitely probably somewhere here in the fourth quadrant. So do a reality check before I'm through here. All right? Now it's kind of good just to keep our feet, about us here. If you're going to add two vectors, okay, just as a reminder, you cannot just add those two numbers, and that is the magnitudes, and you cannot just add the angles, okay? That's not what you can do. What can you add together? The x parts and the y parts, yes. So what we have to do is we have to break this down into its x and y, break this down into its x and y, then we can combine them, then we will figure out what the magnitude and direction is, okay? So it's kind of like a three-step process. 1, split these up. 2, smash them together. Then 3, rebuild it into magnitude and direction, okay? Let's go ahead and do that real quick. We want to figure out what is the x and the y part on this one. So, force vector 1. Do we need to redraw that picture? It's going to be kind of busy here. I'll just redraw it right here. So, I've got a 33-degree angle with 45, and I need to find F1x and F1y. Alright? Seems like I've been kind of doing a lot of the same stuff. What is a formula that might help me find the F1x here, class? Cosine, that's right. So I could say cosine of 33 degrees equals F1x over 45. Multiply both sides by 45. So F1x equals 45 cosine 33. And I know you might want to be like, okay, y'all give me an approximation on that. Give me an approximation. Now I need to find the y part. Here we go. I need a trig ratio that's going to deal with F1y and the 45. Sine. Sine 33 equals F1y over 45. Multiply both sides by 45. You have F1y equals 45 sine of 33. So go and give me an approximation on that one. 44.51. 24.5. All right, great. I've broken this down into its x and y parts. It's 37.74 and 24.51. Now, I need to break this one down into its parts. Oh my gosh, is there a faster way of doing this? No. Well, there is. Would y'all like to know a faster way of doing this? It involves a formula. Because we've got we're all the way down here, it's 322 degrees. And I want to figure out F2x and F2y, right? Okay, well that's 322 degrees, and I've got a right triangle here. I need to figure out what theta ref is right here, right? And somebody tell me, how am I going to figure out what theta ref is? Yeah, 360 minus 322, which is 38 degrees. Okay, so now I've got a triangle, 38 degrees. I need, and that magnitude, by the way, was 75. I need a way of writing a sine or cosine equation that's going to give me f2x. Cosine of 38 degrees is the adjacent over hypotenuse. So f2x over 75. So f2x equals 75 times cosine 38 degrees. What's an approximation on that? 59.1. And then the y component, I need a formula that's going to deal with the y and that angle and hypotenuse. Sine. Sine of 38 degrees is f2y over 75. Multiply both sides by 75, so we have f2y equals 75 sine of 38 degrees, which is approximately 46.17. So here, now I have the x and y parts. I have 59.1 and 46.17. Do a reality check. Does that seem right to y'all?
Yeah.
The y part needs to be negative. Why?
It's in the fourth quadrant.
Because fourth quadrant, it's going down, but the x. No, the x is still kicking to the right, so we're fine. So my calculus or my pre-calculus knowledge is telling me, hey, this needs to be negative. Now let's pause here because I feel like, because honestly, this is the longest part. What we're doing right now, that's the longest part. I mean, there is a way of making this go faster if you can notice that there was a pattern among all four of those things that we did. For instance, when we were looking for the x, which trig ratio did we use?
Cosine.
Cosine. When we were dealing with the y, what formula were we using, or trig ratio?
Sine.
Sine. And if you notice, this one said fx is 45 cosine of the angle. What was 45? The magnitude. Over here, we have 75 cosine of the reference angle, right? And we had 59, and that's how we got our answer. When we look at the y, it was 45 sine, so magnitude sine of the angle. And over here, we end up with magnitude sine of the angle, well, of the reference angle, right? So that's pretty nice. It seems to me that perhaps if we're ever breaking up a formula, breaking up a vector, okay, that we could say that the x component is equal to the magnitude cosine of the reference angle. I'd say the reference angle because that's what we had over here, right? And the y component was the magnitude times sine of the reference angle. Although then you have to keep in mind that you have to do the added step of plus or minus with the reality check, right? Okay? Well, let me show you something that's really neat, okay? You don't need that plus or minus. We can actually plug in the original angle.
Whoa.
Watch this. Instead of saying 75 cosine 38, what if I just said 75 cosine of 322? Key that in here, folks.
It's 59.1.
Is it really 59.1? I need someone else to verify. Not that you're not trustworthy, but just don't trust. I'm talking 59.1. Okay, now here's the real test, Dominic. If I do this, Mr. Goddard says don't even try the theta rep. Just do 75 sine of 322. It gives you, does it?
Yes.
So that's even better for me, because that means I don't even have to think at this point if I'm using the right formula, right? I can use the original angle there, and actually the sine and cosine, because sine is negative in the fourth quadrant. Cosine is negative in the second and third, right? We've talked about that. So here's the beauty of it right here. The x component is the magnitude cosine of the angle. The y component is the magnitude sine of the angle, okay? I don't know why it took us 15 minutes to do all this stuff. I could have just done that part right there.
Yeah.
Okay? Well, I want to make sure you understood how we write that. This right here is like worthy of like tattooing on your like arm, okay? If you're going to be an engineering, okay? But if you're not, then just put it on your cheat sheet. Okay? But this right here, fx is magnitude cosine theta, fy magnitude sine theta, magnitude square root of the sum of the squares, reference angle, inverse tangent of the absolute value of the y over the x. This is huge. Let's go ahead and finish this problem. Believe it or not, it's a bell beater situation. Here we go. What we're going to do is we're going to add the x's and we're going to add the y's. Okay? So I'm going to say, I'll call it force 3, since that's the one thing. That's going to be fx, sorry, the f1x plus f2x. So that's going to be 37.74 plus 59.1. And the y component is going to be the, was that 24.51 plus a negative 46.17. Does anybody have a final answer there for me for the x? I need someone on the x, someone on the y's. 96.84. Negative 21.66. I would say, roughly speaking, that seems to be about what our estimate was. Something a little bit more than 75 on the x, and definitely down a little bit there on the y. Okay? How are we going to find the magnitude? Bing, square root of the sum of the squares. Okay? So, the magnitude is going to be, and you can literally just type this whole thing in the calculator all at once. The square root of 96.84 squared plus, parentheses, negative 21.66 squared. I'm hearing 99.23. Just find that. What about the angle? Theta rep. According to my formula, inverse tangent of the absolute value of the y over the x. So it's going to be inverse tangent of 21.66 divided by 96.84. Theta ref equals 12.61 degrees. This is the only last part. It says theta, it depends on your quadrant. I have to use my head. If I'm in the fourth quadrant, so I'm down here, and I've got 12 right there, 12 point whatever degrees, then the positive angle rotation, theta, is going to be 360 minus that angle. And you're 347.39. Our plan for tomorrow is to do maybe one or two more of these problems really quickly, and then have y'all do one or two at the table and check that, okay? If you're not here because of ASVAB, we will record for you. I think that's going to be senior class.